Indian Academy of Science Summer Fellowship. And if you get it, you can spend 2 summer months in one of the research laboratories in India. So you should keep it in mind. Now your goal is to understand science and do very well in your competitive exam at the end of second year. I want to attend something little more adventurous in this talk. I want to talk to you about 2 aspects which are a little difficult. It is slightly above your standard. This is what you learn in your MSc. But I would like to attempt to see whether I can really convey the spirit of science, not necessarily the technical details of it. It would take a long time to really understand the technical aspect of it. First of all, the goal of science is to understand the world at large. Why is it here? How does it function? We ask questions about the world and we want to find answers. And what we know about the world has essentially come to us through our sense organs. We can touch, we can smell, we can hear, we can feel, but the most important is we can see. So most of our knowledge has come to us because we can see. It is actually a wonderful thing. Eye is a really wonderful thing. It is amazing to note that your eye developed when you were not born. When you were not born, when you were still in your mother's womb, it was a dark world. There was no light there. So, you see, eyes had no real function there because there was nothing to see except your mummy's tummy. Even that is very dark, it is not visible, right? But eyes developed at that stage in anticipation of what is going to happen in the future. And we all have eyes. It is a wonderful organ which tells us about the existence of cosmos. We know that there are stars, billions and billions of stars. We know that our sun is very hot. We know about the planets. We cannot see all the planets with our eyes. We can actually see Venus, for example, very bright spot in the sky. We can see Jupiter with our bare eyes. But there is a limit to what our eyes can see. You cannot see very small objects with our eyes. How small an object can you see? About 1/10 of a millimeter. You have seen the centimeter scale, your ruler. You have seen how small a millimeter is. If you put a dot which is 1/10 of a millimeter, my eyes will not see it, I will assure you. But your eyes can see 1/10 of a millimeter. But 1/100th of a millimeter, even the best eye in the world cannot see it. So there is a limit to what we can see. But a few hundred years ago, scientists invented the microscope. A microscope has a series of lenses which actually shows you an enlarged image of the object. So what your eyes cannot see, you can see some of them in the microscope. This was a fantastic discovery, invention, because as soon as microscope was invented, we came to know that our world is filled with microbes, that is, microorganisms or bacteria. In our body, if you take our skin, there are trillions of bacteria on our skin. Fortunately, these bacteria do not do any harm. If you take your stomach, juice from your stomach, it is full of bacteria. In fact, the bacteria is very essential because it will supply us some minerals, some vitamins which our body itself cannot synthesize. So the bacterial flora in our body decides our health status. In fact, they are very required. Anyway, once it was discovered that there are bacteria, it was also confirmed that the unit of life is a living cell. Although, of course, I say I am living, actually every one of our cells has its own life. It lives independently of us. In some sense, it's absolutely amazing. You know, if we have cancer, you can take the cancer tissue and grow it in the laboratory. It will grow for next 100 years. We may die and go. Our cells keeps growing. But if you take normal cell and grow, it will grow for some time, maybe 1 day, 2 days. Then all the cells will die. For some reason, normal cells don't grow. Cancer cells grow forever. But anyway, cells have independent life, which means you can actually study cells as a unit. And the subject is called cellular biology or cell biology. In fact, at Indian Institute of Science, we have a whole department dedicated to cell biology. This cell biology did not exist before the invention of microscope, because nobody knew that there are bacteria. In fact, we now know that our food goes bad because of microorganisms. We get disease because of microorganisms. We stay healthy because of microorganisms. So they are good and bad. It is both. But again, unfortunately, even microscope has a limitation. The limitation comes because of this reason. Let us say you have a real point, small point source of light. So small, it is absolutely infinitesimally small. Which means nothing can see, you cannot see. Then try to put a lens and, this is the object, there is a point, and you put a series of lenses and you image this. Just like in our microscope, you enlarge the point and image it. Since this point is very small, you think the image also should be a very small object. But actually it turns out that image is not small. The image has a size. So the image has a size like this. That is what we call in physics iris disk. Why it happens? Because light is a form of wave. Because of the wave property of light, even an infinitesimal source of light gets imaged as a small circle. The size of the circle is related to the wavelength of light. It cannot be smaller than the wavelength of light. So our point source becomes not a point, but a ring of size comparable to the wavelength. Now if you have 2 points which are very close, the first point becomes a circle, the second point becomes a circle. If they are too close, the circles will coalesce. The circles will not appear separate. If they are even closer, the image will look like this. Are there 1 point or 2 points here? You would say 1 point because it looks like 1 point. You lose the resolution. We say we lose the resolution. The 2 points appear as if it is a single point, which means you cannot see the points distinctly in the microscope. And how close the objects should be before they become like this. It is about 0.6 lambda, where lambda is the wavelength of light. What is the wavelength of light that we can see? Yes? 400 to 800 nanometer, correct? See, if I put it on here, I hear my own voice. I don't like my voice. I don't want to hear it. So it's okay. Now you see, in other words, if 2 points are separated by something like 400 angstroms, even if you use the best microscope in the world, the most expensive microscope, you cannot actually see them as distinct points. You will see it as a single point. It means that really wavelength puts a limit on how small an object you can see. You cannot see objects smaller than the wavelength of light. Now let us take molecules. We know the world of molecules. Water is made up of 1 oxygen and 2 hydrogen atoms. The distance between oxygen and hydrogen is actually 1 angstrom or 1/10 of a nanometer. It is about 4,000 times less than the wavelength of light. 4,000 times less than the wavelength of light. If wavelength of light is the limit of what you can see, you will never be able to see water molecules. In fact, you cannot see the world of molecules at all using light. This was a problem. We had no idea of what the atomic world looks like. Today you learn about atoms and molecules, and even in your high school you study the structure of benzene. How do we know all these things? Because you can never see it. How do we know structure of benzene is right? Kekule's structure of benzene, you have learned. But how do we know that they are true? Well, the story, you see, it turns out that, from what I said, it is very clear that if you want to see atoms, you should use a light whose wavelength is very, very small. It should not be our visible light. Beyond visible light, there are other lights. If the wavelength is longer than visible light, we call it infrared light. That has a wavelength longer than visible light. If the wavelength is smaller than visible light, we call it ultraviolet light. But there will be light, even smaller wavelength, which we call X-rays, and then gamma rays. They are even smaller, right? On the other side, we have microwaves, radio waves, beyond, longer than. Wavelength of radio waves are meters, the size of this building. Whereas wavelength of X-rays is of the order of 1/10 of a nanometer. That is actually the distance between atoms in molecules. In other words, if you want to see the world of atoms and molecules, you should use X-rays, which have a short wavelength. That is what I want to talk to you about. X-rays were actually discovered about 120 years ago by this guy, Röntgen, a German physicist. And this is his Röntgen laboratory. And, that is his instrument. What he was trying to do, you see, science develops so fast. Today what we have learned, much of it was unknown during the time of Röntgen. Electron was not known. But the nature of electricity was not known. What is electricity? Electricity is a flow of electrons. Do you know? You have studied? Electricity is a flow of electrons. That was not known. But at that time, air is a non-conductor of electricity. It is an insulator. That is why you see, although you have electricity, all these, it won't give me a shock if I take this, because air will not conduct electricity. But if you take a metal rod and put it, you get a big shock, because it's a conductor, right? So air is not a conductor. But if you now remove most of the air from a tube, then at low pressure, you cannot remove all the air. You cannot create vacuum. That would be very, very difficult. As you remove, some air keeps going inside, so you have to pump out very fast. Then you can create an ultra-high vacuum. Then, actually, you can pass electricity through air. But you have to apply very large voltage. For example, this, what is written here, cathode, is a tungsten filament. You can heat this filament by passing a small current through it. The tungsten gets heated. It is like our electric stove. You have seen cable in the electric stove getting red hot. Like that, in old days, you wouldn't have seen. There were bulbs which had tungsten filament. So if you switch it on, the tungsten filament will get hot and emit light. They are not very efficient bulbs, but there were bulbs of that kind. So the cathode, if you now pass an electricity, it becomes white hot. And then between, this is what we call anode. Anode means which is at a positive potential with respect to cathode. Which means in a battery, you connect the positive side to this and negative side to this. Except that the battery should carry 50,000 volts. The battery that we have, pentas battery, is 1.5 volts. But, creating 50,000 volts is a trivial job. Electronics will tell you how to create 50,000 volts. So you apply 50,000 volts between cathode and anode. Then, today we know that any metal that is white hot will be emitting lots of electrons. Of course, during Röntgen days, electrons were not yet discovered. So he didn't know it was electrons. It was a blind experiment. But because lots of electrons are getting emitted from the cathode, they get pulled by the positive potential, positive voltage. And they all come running towards the anode. When they hit the anode, they lose all their energy. And that energy is converted to electromagnetic radiation. And that energy, 50,000 electron volt energy, is in the X-ray region. Because energy of electromagnetic radiation is given by the formula E is equal to h nu. The more the energy, the higher the frequency or lower the wavelength. So 50,000 electron volts corresponds to X-ray region. So X-rays will come out of the tube. The X-rays will come out of the tube. In fact, in modern tube, there is a tungsten, there is a beryllium window through which X-rays will come out. And he didn't know, he knew that some kind of rays are coming from this tube, so he called it X-rays because he didn't know what they are. He didn't know that they are electromagnetic radiation of very short wavelength. But his wife was always with him whenever he did his experiment. So he asked his wife to put her hand in the beam of X-rays and put a photographic plate there and develop the photographic plate. Lo and behold, that is the picture he got. If you look at this picture, that is the wedding ring of Mr. Ranjan. This hand is immediately clear that X-rays pass through muscle much more than bones. So that shadow of bone is cast on the screen. It's exactly like shadow of our body is cast on the ground if you stand under sun. Except that the shadow here of the muscle is lighter than the shadow of the bone. Which means you can see the bone. You see, without cutting the hand, cutting the body, you can see the inside of the body. Isn't it amazing? In fact, within 2 months, X-ray machines were used in hospitals to see if there is a broken bone. The application of a scientific discovery and the discovery itself is so sharp. Within 2 months, it was already in the application. It is absolutely marvelous discovery. What happened? I don't know whether I pressed something. Can you expand? Yes. So actually, at that time, he didn't know what X-rays are. On a parallel side, there is some other story. Our country is very famous for crystals. You may not know. Even today, if you diamond is not very much available in India. It's available in Africa. And when they get diamond ore in Africa, they send it to India, to Rajasthan. In Rajasthan, they polish the diamond. That means they cut the diamond into various phases. Then only it becomes very beautiful. The raw ore is not as valuable. And then it gets sold in the Middle Eastern market because none of us have money to buy diamonds. You see, only the oil-rich countries people buy diamonds. So they get sold in. So crystals were very fascinating to Indians. They studied a lot about crystals in ancient India. I have a whole story to tell you about what was known in India about crystals. Really, we can be very proud of. The science of crystallography was developed to a very high degree in India. But I am not going to talk about it. In fact, actually, in Indian languages, it was called Ratna Shastra, the science of diamonds, science of precious stones. So, a lot was known about this. And you see, crystals are beautiful. They have very definite shapes. Their faces are at definite angles. Why do crystals are like that? That was a scientific question. Why does diamond has, if you already have heard of it, tetrahedral symmetry, octahedral symmetry. You have heard of it, right? Even if you haven't heard of it, you will hear. Don't worry about it. Octahedral symmetry is a very highly symmetric object. It is the symmetry of an object which has 8 faces, 6 vertices and 12 edges. Anyway, diamond was known to have octahedral symmetry. So each crystal has its own symmetry. Why do crystals have symmetry? Then people made a theory. And that theory is that crystals are periodic arrangement of molecules. Just like there is a periodic arrangement of all of you here, the chairs are periodically arranged. Which means the distance between any 2 consecutive chairs is maintained to be the same value in every row, the distance between one row and another row. You see, this way also the distance is maintained, this way also the distance is maintained. So this is a regular array of chairs. Like that, people thought if molecules are regularly organized, we can account for the properties of crystals. Why crystals have some shape. For example, if molecules are going along this line and going along this line, maybe in the crystal also there will be a face this way and a face this way. The two faces are at 60 degrees to each other, whatever. The external morphology of the crystal reflects the internal arrangement of molecules in the crystal. This was an assumption. Because nobody could see what a crystal is. How do you see inside of a crystal? To see inside of a crystal, you have to see molecules. To see molecules, what do you have to have? Light is not enough, because light has too large a wavelength. Well, you see, it occurred to one very brilliant physicist, Lave, that if crystals are really periodic array of molecules, X-rays are really electromagnetic radiation of short wavelength. If you shine X-rays on crystals, the crystals should scatter X-rays in some directions, but not in all directions. See, this is contrary to general scattering. You see, I am standing here, but I know that all of you can see me. You can see me because the light scattered from my body is reaching your eyes. You put your hand in front of your eyes and cut off the light coming from my body to your eyes, I vanish from your sight. You won't be able to see. I cannot see any of you now, because the light scattered from your body is not reaching my eye. So one requirement for us to see is that the light scattered from the object should reach our eyes. Since all of you can see me, it means my body is scattering light in all the directions. If it is not scattering in this direction, none of these people will be able to see me. But that is not the case. So it goes to show that my body is scattering light in every possible direction. But Lave argued that if crystals are periodic and X-rays have a very short wavelength, then crystal will scatter in this direction, but not in the intermediate directions. That means scattering will be discrete, not continuous. The scattering from my body is continuous, it's in all directions. But scattering from a crystal will going to be discrete. That is what he theorized. This happens only if both of them are true. Crystals are periodic and X-rays are short electromagnetic radiation. Then two of his students, Frederick and Dipping, produced X-rays, took a crystal and took a picture. And can you see that it has scattered here one spot, scattered here one spot, here one spot, here one spot. It hasn't scattered in between. So this was the proof of Lave's idea, and Lave got Nobel Prize. There are many people who got Nobel Prize. I won't list all of them. So this was the beginning. Then there were two people, equally great scientists. Well, actually, you see, now the whole science is based on such precise mathematical description. If you are given a crystal and hit it with X-rays, which are the directions in which X-rays get scattered and which are the directions in which X-rays are not scattered can be worked out with these formulae. To understand this formulae, you will have to, there are three different formulae here, and to understand all these formulae, you will have to wait another 5-6 years. It takes time to understand. But these will tell us, if you know how to use this equation, you will be able to figure out which are the directions in which a crystal will scatter X-rays, which are the directions in which the crystal will not scatter X-rays. This is what you can call theory of X-ray diffraction. Okay? This process is not called scattering, but it is called diffraction. Because in some directions, the waves scattered by the crystal, because X-rays are electromagnetic waves, they add up. In some, they cancel each other. So they will become large amplitude in some direction, no amplitude in some other direction. Then a father and son team, Bragg and Bragg, realized that if you measure the intensity coming in different directions, and some more information. What that information is, I will tell you in a minute. If you see, after all, if you have a crystal hitting with X-rays, it will scatter in this direction, it will scatter in this direction, but it will not scatter in between. If you now measure how much X-rays are coming in each direction, and plus some more information, you can actually figure out the structure of the crystal. That means you will be able to figure out the atomic structure of the crystal. That was the idea of the father and son. And what they determined is the structure of sodium chloride, which you have studied in your primary school. It was only 104 years ago that they actually worked out the structure of sodium chloride. Before that, nobody knew what the structure of sodium chloride is. In sodium chloride, a sodium sits between 6 chlorines, and a chlorine sits between 6 sodiums. You know the structure. You study it in primary school. Almost primary school kids are taught this. But this was a momentous discovery, and father and son were awarded the Nobel Prize for discovering the structure of sodium chloride. Well, it was established then that X-ray scattering can actually reveal us the structure of materials. But then you see, can you build a microscope using X-rays? That was not possible, because to build a microscope, you have to have an object plane, you shine light, and scattered light, you put a lens and bend the light to make the image plane. But X-rays, there are no lenses that bend the X-rays. And the objects we want to see, molecules, if you take a single molecule, it will scatter so little X-rays that the scattered rays will not be detectable. Whatever it is, technically you cannot build a microscope. That was clear. So you have to see the world. If you want to use X-ray eyes instead of visible light, the technique has to be different. It cannot be just microscopy. So the science of X-ray diffraction started with Bragg and Bragg. I will just tell you how much this subject has progressed in the 100 years. See, whatever Röntgen produced X-rays, remember what you have to do. Heat a filament, it emits electrons, accelerate it with a voltage, it hits the anode, and the anode scatters X-rays. If you want to produce more intense X-rays, you have to produce more electrons, and more electrons should come and hit the anode. Then problem is, when lot of electrons come and hit the anode material will melt. It may be copper, but it will melt. So there was a limit to how much X-rays you could produce. Almost for 70 years, people could not produce X-rays of higher energy, higher flux. Flux, you study flux in your optics. You may have studied, or you will study in this year. Flux is the energy density of your light beam. The energy density of X-rays was limited. But in the 1970s, people developed a so-called rotating anode. I don't know why it reverts back. You see this copper, the target, copper target, this was in the form of a cylinder. And that cylinder was being rotated. So the filament is here, electrons are bombarding the anode, and the anode itself is rotating. So that different parts of the anode are hit by electrons at different times. So the heating effect is reduced. So you could produce 10 times more intense X-rays. But as it always happens in science, see, when we divide science into physics, chemistry, biology, it is because our lifetime is limited and we have limited time to study. But really there is no distinction in science. It's all one big branch of knowledge. So actually what happened, physicists were actually building some machines called synchrotrons. The other physics people's experiment, high energy physics, there's a branch called high energy physics. They were building so-called synchrotrons. And I am sure you have heard of Large Hadron Collider, or the discovery of the God particle 2 years ago, right? Higgs boson, discovery of Higgs boson. That also is a machine similar to this. in this machine, what physicists used to do, you see there is a kilometer. The machine is so big. The machine is of the size of a kilometer. So if you want to take a photograph of the machine, you have to go in a helicopter and take a picture. Because you cannot stand in front of the machine and take a picture. The machine is 1 kilometer long. This is a kilometer, more than a kilometer, this circumference. And here there is a tube inside the ground. And inside the tube of this size is completely evacuated to the 10 power minus 9 atmosphere pressure. Evacuated tube. In the tube, electrons go round and round. And they are made to go so fast that they will be almost going at 300,000 kilometers per second. Which means in 1 second, they will go around the earth 7 times. 7 times they will go around the earth. It is at that remarkable speed, electrons will go round and round and round this tunnel. And when electrons go round in a circular path, they produce very intense X-ray beam. It is 1,000,000 times more intense than what a rotating anode can produce. These machines became available in the late 80s and early 90s. You know, that is just before you were born, or maybe a decade before you were born. It's not that old a science. And when physicists made these machines, crystallographers went there and said, "Yo, no, you physicists go away from here, we will use it for our diffraction experiments." So they started using X-rays from synchrotrons. So, you see, I worked on viruses, and in Bangalore, to collect X-ray diffraction data on viruses, we worked for 3 years. Because the beam was so weak, each photograph will take 40 hours exposure, and we had to take hundreds of pictures. But if you go to synchrotron, you can do it in 1 hour. So whatever you could do in 3 years, now can be done in 1 hour. That is the advancement of science. And this advancement to crystallography has come from physics, because physicists developed synchrotrons. Alright? So actually, if you now expose a virus crystal to synchrotron, you will get a photograph like this. And there are so many spots. You see, these are the directions in which the crystal has scattered X-rays. I told you that if there is a lava discovered, the crystals scatter in some directions, but not in others. So the directions in which it has scattered, that has a spot. But the other directions don't have a spot. But to determine the structure, I told you, you have to measure the intensity of each of these spots. Now, if you count the number of spots, it's almost like counting the stars in the sky. Each photograph has something like 10,000 spots. But I put a virus crystal, hit it with X-rays. Then I rotate the virus crystal, hit it with X-rays. Rotate the virus crystal, hit it with X-rays. In all directions, I hit the crystal with X-rays, and every time I hit, I get a different photograph. So I get 500-600 photographs. Each photograph has 10,000 spots. I have to measure the intensity of each one of these reflections. How am I going to do it, you know? Even if you do it for a lifetime, you won't finish it. Well, fortunately, as I said, there was a development in computer science and automation. You know, in a way, earlier, in fact, I have done it as a student, I have measured the intensity of these spots using my own eyes. But that was for a small molecule. But now, you can just feed this picture, this photograph, into a computer and ask the computer to locate where the spots are. You know, you don't worry about it. The computer will find out where the spot is. And ask the computer to find out how much intense the spot is. So actually I can ask the computer these questions. I can ask, where do you come from each spot? Which face of the crystal sent you here? You know, one face of the crystal has caused the reflection. I can ask, how strong are you? That means, what is your intensity? How much do I trust you? What is the error in my measurement? All these have been automated. So you don't have to, even if you have 600 photographs, on a computer, in 1 hour on a desktop computer, it will process all the photographs and give you 5 million reflections. You know, intensities of 5 million reflections. You know, structural ribosome was determined in a few years ago by Venki Ramakrishnan, for which he got Nobel Prize. They measured 30 million. 300 laksha, 30 million, that is 3 crore reflections. They measure intensity of 3 crore reflections to determine the structure of ribosome. This wouldn't have been possible without advances in computer technology. You see, image processing anta there is a field which you will hear about. This image processing is done starting from film industry to science. See, many, I don't want to digress, but many of the films that you see or cartoons you see are all computer animations. It's not necessarily drawn. You can do it all this in computer. You just have to wait a few years and learn some computer science. Then you will be animating your own pictures. Anyway, all this can be processed with computer. But there was another problem. You see, X-rays are very dangerous rays. Once they hit any material, they will ionize. They are called ionizing radiation. If the radiation has a lot of energy, it will create ions. These ions will destroy your crystal. So when you irradiated a crystal with X-rays, the crystal was getting destroyed. This was a perpetual problem. In fact, when we were doing virus work, we take one crystal and take one picture. By then the crystal is dead. For the next picture, to hit it in some other direction, we had to mount another crystal. So we had to mount something like 80 crystals. But how do we protect the crystal from radiation damage? Was a big problem. Then some clever guy discovered that if you put your crystal in a beam of liquid nitrogen or nitrogen gas at 100 degree Kelvin or minus 273 degree Celsius. 100 degree Kelvin is minus 273 degrees Celsius. If you cool the temperature to 100 degree Kelvin, then X-rays do not damage. They create ions, but the ions don't move in the crystal. They are immobile, so they don't destroy the crystal. So you could collect all the diffraction data with a single crystal. Whereas earlier, since crystals were damaged by radiation, we had to use many, many crystals. But that made a big difference. Then earlier, we used to record our X-ray diffraction patterns on photographs. I think most of you wouldn't have seen a regular photographic film. See, earlier, even our photographs were actually recorded on silver halide films. They are very slow. Now you see these mobiles can take pictures. I am sure all of you have taken pictures on your mobile. But they are really electronic detectors. And the detector technology was actually developed for X-ray diffraction much earlier than it was actually developed for commercial photography. These detectors are much, much more sensitive than silver halide screens. That also speeded up our data collection. Well, then there were actually developments in biology. See, if you want to study a molecule using X-ray diffraction, you should have crystals. Without crystals you cannot study. But how do you get crystals? To get crystals you have to purify. How do you purify? That becomes very difficult. Some purification you have done at home. If you buy, for example, say for a rice, there may be small stones in the rice. How do you separate it? You don't have to tell me, you know already. And mustard, have you cleaned mustard? Mustard, mustard. Do you know how people clean mustard at home? Remove all debris? Huh? Well, you ask at home, you will find out. Well, that's very easy because probably mustard is mixed with some mud or something, small impurity. But if you take any part of our tissue, there are tens of thousands of molecules. How do you purify one molecule out of all the other molecules? It's not a simple technique. In biology, you learn the so-called chromatographic techniques. They are really, really powerful techniques that will allow you to separate one molecule out of tens of thousands of other molecules. So using chromatography, we can purify whatever we want. Next slide. Well, you see, sometimes proteins, let us say you purify is okay, but how can you purify a protein from, let us say, influenza virus. Influenza, you cannot get a lot of influenza virus to purify the protein. You see, first of all, when somebody has flu, there is hardly a small, microgram of influenza virus in his body, whole body. You cannot kill the whole person and extract virus. It's not possible. The only possibility that we have today is what we call molecular biology or genetic engineering. We can cut the gene of coding for any protein from any organism and clone it into a bacterial expression system. And then from this bacteria we can get the protein. This technology has revolutionized everything that we do. For example, lots of people in our home suffer from diabetes and they need insulin injection. But if you want insulin, what you should do? Take these girls, kill them, take their pancreas, extract insulin, because insulin is in their pancreas. Pancreas is a small organ. 5 pancreas, I can get enough insulin to help my mother for 1 month. What about years? How many people should I kill? It's not necessary. All that I need to do is to take the gene coding for insulin, put it in a bacteria and ask the bacteria to make insulin. Bacteria makes human insulin and that is in the market. You go to the medical shop, you can buy recombinant insulin. That is through molecular biology. And that molecular, cut it off. That actually has made possible for us to get anything, any protein of our choice. There is one more problem. See, you have to get crystals. How do you grow crystals? It would have been very nice if we can grow any crystal of our choice. For example, diamond is only carbon. Graphite is carbon, diamond is carbon. There are different allotropic forms of carbon. This you have studied. If you can convert graphite into diamond crystals, you will be the richest person on earth. How wonderful it is. But crystallization is a very tough job. You don't know under what condition it is going to crystallize. See, in principle, there is nothing theoretically that prevents you from converting graphite to diamond. In fact, you can destroy diamond very easily. Put it in an oven and heat it up. Diamond just burns into carbon dioxide because it's just carbon. But anyway, making diamond is a very tough job. Similarly, making crystals of all materials is a very challenging job where it takes a lot of time. But then people develop robots which will actually explore different conditions for crystallization. So we can actually make crystals. So you see, every step of determining the structure and seeing the molecules has undergone tremendous advancement over the last 60, 70 years. But, so actually now today, if you want to look at the structure of any molecule, let it be an organic molecule, all drugs are simple organic molecules. Aspirin or, Brufen, for headache you take Brufen, ibuprofen. They are all very simple organic molecules. About 100 or 200 or 300 Dalton molecular weight, containing 10 to 12 atoms. Most drugs are very small molecules. Whether it is the structure of a drug molecule or structure of a protein or structure of a virus, big structure or small structure, the methodology is the same. First, you have to purify whatever you want to study. Then you make crystals. Then you go to the X-ray lab, put the crystal and heat with X-rays. Then you will get diffraction pattern. And then you have to measure the intensity of each of these spots. And depending on how big your molecule is, the number of spots will vary. For a protein, for a small molecule like benzene, there may be 300 spots. For a protein like a virus particle, there will be 3 million points. You will have to measure the intensity of each of these. Then you can use all these intensities plus some other information which I will tell you in a minute. You do a lot of calculation. This is so much calculation that if you have to do manually, If you had started at the beginning when the world started and did it till today manually, the calculation will not be over. It is that kind of huge calculation that is possible because we have super duper computers today and they are available at a very low cost. You know, when I started my research career, computers were not in the market. IISc did not have a computer. And then it acquired a computer and as I entered IISc. I have grown up with computers. Still the fascination of these wonderful machines does not go away. What they can do is amazing. And if you don't learn to use computers very well, I would say you are illiterate. You know, by learning I, E, or A, B, C, D, you don't become literate. You become literate only when you learn computer programming. Alright? That is the modern definition of literacy. Computer literacy is true literacy. I don't know how many of you are literate yet, but if you are not, try to be literate. Alright? You go to computer class or learn on your own, have a laptop or a computer at home, learn. You know, it's absolutely important. So you do a lot of calculation, you will actually see your molecules or you will witness your molecules. It's absolutely fascinating. We can learn about the world of atoms and molecules. But there is a small problem. See, each of these parts is a wave, X-ray wave that has come. And waves have some property. If you take, for example, this wave and this wave, we say these two waves are in phase. So, which means that when they meet together, see this crest of this wave falls on the crest of this wave. When these two waves meet together, we get a very big wave. Whereas you see this wave and this wave, the crest of this wave falls on the trough of this wave. We say these two waves are out of phase. When they meet, they will cancel each other. 1 plus 1 equals 0. Whereas there, 1 plus 1 must 2. But you see these two waves, the crest of this doesn't fall quite on the shallow region of this, but somewhere in between. So these are partially out of phase. Then 1 plus 1 will not be 0, but it will be less than 2. So you see, when you add waves, what happens depends on the relative phases. What is the phase difference between the waves? So each of the scattered waves in our previous picture has a phase. And you have to take into account that phase also. Then only you get the structure. So you will have to determine those phases. That's what I have illustrated in this picture, but I can as well skip because I have already told you. If you shine, let's say X-ray on a cat hole, you will get a pattern like this. I can say the intensities represent the amplitude and color represent the phase. But in reality, you get only this picture. You get amplitude, you don't get the phase. But if you take this picture, we can say that it has come from a cat. But if you take this picture, unless you find the phases, you cannot say it has come from a cat. This is what we call phase problem. So those waves have phases and you have to find. And people have developed various methods to find phases. I won't go into the detail. Anyway, it's beyond the scope of this lecture. But just suffice to say that people have developed methods to find these phases. Each of the person who developed these methods has won the Nobel Prize because it's such an important problem. And as I have listed here, you see Nobel Prizes for so many people. And that has actually given us this whole ability to look into the world of atoms and molecules. It will only just give you what we have learned. And so these are the 20 amino acids of which our proteins are made of. You know, our body is made up of millions of molecules, actually not one or two. But the major large molecules are proteins, nucleic acids, carbohydrates. Proteins are polymers of amino acids. They are made up of 20 amino acids. The structure of each of these 20 amino acids has been determined by X-ray diffraction. It means we have looked into the structure of these molecules because of X-ray diffraction. I have just illustrated two examples from my own laboratory. This is a molecule which actually works, this is called propionate kinase. It's an enzyme. Enzymes increase the rate of chemical reactions. They are catalysts. You know, that's enough for you to know just now. This is a large protein. The structure of the protein has been determined. This is a virus. It infects plants. And the structure of the whole virus has been worked out. See, from small molecules to viruses, you can actually determine the structure. How many structures have we determined? If you take organic molecules, I told you all drugs are small organic molecules. In 2012, the number of structures determined was 6 lakhs. 600,000 structures had been determined, and the number of structures determined. You see, actually, 1972, when I started my research career, there were hardly any structures. Today, there are more than 600,000. Not 600,000, more than a million structures. More than a million structures we know. And all these million structures are useful for us. This plastic, what is the structure of this plastic? What is the structure of this fiber? Starting from there, you can ask structure of anything. How many chemicals are there in your lab? They are just maybe 10, 15. But we know the structure of more than a million compounds. How these compounds can be used for your and my benefit is left to you. If you are a good chemist, you can actually use all these structures and make something very useful. But proteins, if you take proteins, which are really big, compared to organic molecules, we have determined more than, today we have determined, this 2016, if you come to 2018, it has exceeded 1.5 lakh protein structures. So these proteins from all organisms, from viruses, bacteria, prokaryotes and eukaryotes, every organism, we have determined so many structures. So X-ray diffraction has become a very powerful tool for us to see the world of atoms and molecules. See, in your class now, you will start learning the structure of atoms and molecules. Chemical bonding, why does carbon make 4 bonds, oxygen has a valency of 2, all these rules you study. But what is the proof? The proof is X-ray diffraction. You can actually work out the structure of these molecules and verify for yourself that what you study in your textbook is practically valid. Alright? That's how much I want to tell you about X-ray diffraction. Tell you how. Now, I want to tell you about another technique which is becoming almost equally powerful as X-ray diffraction. You have learned the structure of atoms. I just want to remind you that every atom has a nucleus. And the nucleus has protons and neutrons. Around that, electrons are going round like the planetary system. This is what you learned. But I will tell you there is a problem. Electron is not like Earth. It is not a particle. You think electron is like Earth, it is going around there. But electron is a cloud. Actually, electron has properties of waves. This was actually proposed in 1924, less than 100 years ago, by a French scientist called de Broglie. He called it electron waves. Electrons are not particles, they are waves. Light is not a particle, it's a wave. But today we know that light sometimes behaves like a particle. We call it photon. When you want to refer to the particle nature of light, you say photon. When you want to refer to the wave nature of light, you say electromagnetic wave. So, we don't understand really, but somehow it behaves sometimes like waves, sometimes like particles. Because light behaves both ways, de Broglie argued that maybe electrons also behave both ways. Sometimes they look like particles, sometimes they may look like waves. So he actually worked out a formula. How he arrived at this formula is slightly beyond the scope of our discussion. See, if you want to have the wavelength of electron wave, electron has to be accelerated by applying a voltage. Electrons are negatively charged. So they start jumping towards the positive electrode. If you put 2 electrodes, one negative, one positive, electron will start moving fast towards the positive electrode. As its speed increases, the wavelength associated with it becomes smaller and smaller. So actually the voltage that you have applied, 150 divided by voltage power 0.5 into 0.1 will give you the wavelength in nanometer. For example, if the voltage is 100,000 volts, the wavelength will be 0.005 nanometer or 0.05 angstroms. It is as sharp as X-rays. But electrons are not like X-rays. There are lenses for electrons. So electron waves can be bent. X-rays cannot be bent. In other words, electron waves are like light waves, not like X-rays, which cannot be bent by lenses. Electron waves can be bent. You can bend it by lenses which are not made of glass but made of magnets, electromagnets. Electromagnets can bend electrons. So in principle you can build electron microscope. So as soon as de Broglie proposed electron waves, it was realized that you can build perhaps an electron microscope. In fact, one famous scientist, Leo Szilard, suggested to construct an electron microscope. But the student retarded. What is the use? Because electrons burn up everything. If you shine electrons onto a material, it will burn the material. It will destroy the material. So everything under the electron beam will burn into cinder. What is the use? He didn't believe that it is possible to really do a microscope. But scientists don't give up so easily. Just a few years afterwards, Ratzka built the first electron microscope. Here it is exactly like your optical microscope. You don't have to learn anything more. You have a source of electrons, you put the object, it scatters electrons, then instead of glass lenses, you have a series of electromagnetic lenses, then you have an image plane. Generally, it is viewed the other way. The electrons come from here, and image plane is here, the object plane is here, and image plane is below here. So it is like inverted. But anyway, it's exactly like an optical microscope, except that instead of light, you use electron waves. They built it. He built the electron microscope in 1932, Ratzka. He was awarded Nobel Prize in 1986, 55 years afterwards. That is because, you see, as Gabor had pointed out, electrons will burn everything. So how to use electron microscopes without burning your sample? That was a big challenge. And this challenge had to be overcome before electron microscope became really useful. That is why it took so long a time for Nobel Committee to recognize the contribution. But every one of the problems was actually sorted out in the intermediate time. So here is a drawing, kind of block diagram telling how the electron, parts of the electron microscope. You have an electron gun. It is exactly like a source of light, bulb. And then you have a condenser lens. Then you have some few other lenses. Then you have a specimen here. And then you have a series of lenses, and you have an image. You have an image plane where the image is formed. So it is exactly like our optical microscope, except the lenses here are all electromagnetic lenses. But the advantage is, you see, actually, I have a little bit elaborate picture. Electrons are ejected either with a filament, like in X-rays. You see, tungsten filament, if it is hard, it will eject electrons. We also have so-called, there are, it can be filament or it can be an electron gun. And then we have to apply a voltage so that the electrons speed up to have a specific wavelength, and they come here, streams of electrons originating. And then the advantage here is that this is an electromagnetic lens. When the electrons pass through this, they are focused onto the object or image plane. But these electromagnetic lenses are so wonderful. In an optical microscope, the focal length of the lens decides how the microscope is going to work. You will learn in your +2, if not +1, you will learn what is the relationship between focal length of the microscope and magnification of the microscope. You know, the arrangement of lenses in a microscope you will be learning. If you haven't started learning already, have you started learning already? You will learn. In +2 you will learn. But there, the focal length of the lens is a fixed quantity. You cannot change it. But in electromagnetic lens, just by changing the current, you can change the focal length of your lens. So it is like length of variable focal length. So it's much better than the lenses that we use in optical microscope. Because electrons are so destructive rays, and see, destructive means they interact with matter and get absorbed, and the energy goes to destroy the matter. So you cannot actually view any sample which is thick, because it will be completely absorbed. Electrons will be completely absorbed. You have to have extremely thin specimens. You cannot actually put a cockroach and view it in an electron microscope, because cockroach will absorb all the electrons. It will essentially be dark. You have to have an extremely thin sample. How do you get thin samples? This was a big problem. I told you that they had to overcome many problems. Now what they do is to have this kind of copper grid. You see, this is a copper grid. This is a copper plate. This plate is of the size of this button really, or slightly smaller than this button. And in this there are small holes. There are holes here. So this is called a holy grid. H-O-L-E-Y, holy grid. That means there are little holes in this grid. And you put a very thin layer of carbon on these holes. And then you actually load your sample onto this very thin layer of your sample. For example, you can take a virus, a drop of water containing virus, put it on the grid and absorb all the water through a fish paper. But it leaves a layer of virus particles on the grid. Then you can put it on the microscope and you can image it. This is an old microscope, and now you see all the lenses are here. Your sample is here with the grid on which you have loaded virus particle, and then you have an image plate here. Actually, the top here is Sesbania mosaic virus on which we have worked. This was photographed in a Philips microscope at the Indian Institute of Science. This is the first electron microscope recorded ever in the world in the mid-1950s by Alan Clun. And this is a virus particle of tobacco mosaic virus. You know, tobacco mosaic virus was discovered more than 110 years ago. But the first image of tobacco mosaic virus was obtained only in 1955, because that is when electron microscope became available. Why you could not see viruses in an optical microscope? Viruses are much smaller than the wavelength of light. But electrons have a much smaller wavelength. So you can see them in an electron microscope. So we could see, you could see this was the benefit, first benefit to biology by electron microscope. See, it took our world, our world product. Our world was limited to what eyes can see and the microbial world which microscope can see. But now it expanded into viruses, sub-microscopic particles. They are called sub-microscopic particles because they are beyond the scope of seeing it in a microscope. So it was fantastic. You see, actually a lot of insight into biology was obtained by very clever application of electron microscopy. See, this is tobacco mosaic virus, and how does this tobacco mosaic virus particle is assembled? This is how it is assembled. Each banana-like object here is a protein subunit, and this is an RNA molecule that stores the genetic information of tobacco mosaic virus. And the structure of this virus could be worked out by very clever use of electron microscopy. That means it was not an X-ray diffraction, but it was electron microscopy. Then the problem with electron microscopy was that, this is, I will tell you, it is the problem of contrast. What I mean is, if you have a glass plate thin glass plate, put it in a glass of water. Can you see the glass plate very well? You cannot see a glass plate inside water. Why? Because the scattering by water and scattering by a glass plate are more or less the same. We say there is no contrast. Well, see this room, just to illustrate this, in this room there is a glass partition, but there is one place where there is no glass partition, so that you can walk inside. And where is that place where you can walk in? Well, you see, if you actually go to that room, maybe you will think that it's a door and walk through and hit a glass, and then you realize that it is glass. That is because the scattering by air and scattering by glass are nearly the same. There is no contrast. Perhaps the door is here, so people can go inside and work there. And all these, if you are at some angle, the glass is visible. But at other angles, the glass is almost not visible. See, sometimes you cannot tell whether the window has a glass shutter or not. The glass is very clear. In fact, when you drive your car, you never realize that there is a windshield in front of you. You never see it actually, because the contrast is not there. This was a big problem in electron microscopy, because the scattering by the carbon film was the same as this scattering from the sample. In the beginning, what they did to increase the contrast, you take the biomolecule, let's say a biomolecule, then you add a metal oxide like phosphotungstic acid. Tungsten scatters electrons very powerfully. But if your particle is embedded in this metal thin sheet, then you see all here the metal will be thicker and here it will be thinner. So that at the dark background you see a white particle. This is called negative stain. This kind of technique was used in the beginning to look at biomolecules. But this had a problem. The moment you stain, the biomolecules will change its shape. So what you see was not real. This was a big problem. You see, the moment you see it, you have distorted it. But then people did the same trick, how to actually keep the sample without negative staining, but use it in an electron microscope. They realized that it is possible if you cool your sample to liquid nitrogen temperature. That microscope had to be developed, and that is called cryo-electron microscope. This is an electron microscope, but the sample is held at 100 degree Kelvin, at minus 273 degrees Celsius. Then electrons will not destroy the sample as much, but there is hardly any contrast. Can you see the particles here? Can you see the virus particles here? They are virus particles. But, to really develop this cryo technique was so difficult. This guy, Debauche, was awarded Nobel Prize for just working out how to actually cool biological samples to liquid nitrogen temperature and put it into an electron microscope, which retains the temperature. He was awarded the Nobel Prize for the technical development of this. But you will get pictures with very low contrast. So how to reconstruct the image? Well, electron microscopes are very, I will skip. See, when you take an electron microscope of a biomolecule or any molecule, the molecules are sitting on the electron microscopic grid. See, some molecule may be sleeping like this, some molecule may be sitting like this, some molecule may be sitting like this. They are sitting in all orientation. And when you take a picture, you get hundreds of particles. So some particles are like this, another particle is like this, another is like this, another like this. So you will have to put them all together and then recognize that, you see, for example, this picture and this picture are one and the same. This and this are one and the same. Combine them and you will get a large number of pictures which are two-dimensional images. To combine these two-dimensional images and get a three-dimensional image is a big technology. If I photograph you from different angles, in principle I have information about your three-dimensional structure. But how to get that three-dimensional structure is a very big challenge. And that has been solved completely in the last 2 decades. So I just want to illustrate that. See, there's a duck here. You take a picture of the duck. Stand here and take a picture of the duck, you will get a picture here. Come in front of the duck here and take a picture, you will get a picture here. Go to the back of the duck and take a picture here. Can you combine these and get back the duck? That is the question. This is called three-dimensional image reconstruction. This is a very hard technique, and you will have to learn a lot of maths and computer programming to be able to do it, but all this has been achieved. So it is possible today to take an electron micrograph and construct the three-dimensional image. Let me actually tell you, the first success of this came in the 1990s. I don't think you were born in 1990, but around 1995 or so, he also got Nobel Prize 2 years ago. Anderson, for doing the structure of so-called bacterial rhodopsin using electron microscopy. But how science proceeds, I want to give you the last example. See, actually, it's amazing. There was a disease of, you have heard of Uganda, the country in Africa called Uganda. In 1947, when India got its independence, you see 1947, some people in Uganda had a strange fever. And people wondered what this fever is. And they collaborated with, Uganda did not have a great scientific laboratory. They collaborated with some people abroad and found that it is because of a viral disease. And that virus was in African monkeys. The virus was in African monkeys. And some Africans eat monkeys. It's not a very, very surprising thing. Monkey is a very edible animal in many parts of Africa. And half-cooked monkey when they ate, they actually got this infection. Somehow it was transmitted zoonotic because zoonotic viruses. It is transmitted from animals to humans. So that place in Africa is called Zika Valley. Zika Valley. So the virus was named as Zika virus. Zika virus. That was in 1947. Then, of course, people told, Ugandans were told, if you want to eat monkeys, cook it well. Don't eat just half-cooked monkey. Anyway, the disease didn't appear again, and we forgot about it. Then, almost 30, 40, 50 years afterwards, there's an island here. See, Africa is here somewhere. There's an island here. This is India, there is Singapore here, and just above Australia there is an island called Yap Island. This Yap Island actually belongs to America, and a lot of Americans go there. There are only 2,000 people or so in the Yap Island. It's a tourist destination. And some people in the Yap Island got fever. The fever will stay for a week and go away. It was a lot of irritation, itching, but it will go away. And they found that it is Zika virus. The disease causal agent, because it's an American colony there. So they immediately did the test and found that it is Zika virus. So what was Darwin for almost 60 years appeared in Yap Island. Then it spread quickly to all these East Asian countries, Singapore, Malaya, Sumatra, Thailand. In all these places, people suffer. Of course, they actually did some work. Nobody bothered because Zika virus caused irritation and fever for a week and then it will go away. See, like common cold virus. See, common cold virus, you get runny nose. After a week, whether you take drug or not, it will go away. It's not that serious. So nobody bothered. But then, you see, actually, in Brazil, 2015, we come very close. 2018, just 3 years ago. In Brazil, there was Olympic Games. And all the stalwart players of the world were coming to Brazil. And all of a sudden, there is an outbreak of Zika virus in Brazil. What do you do? All these great players are coming to Brazil. And what if they get Zika viral infection? How will they compete? The world woke up. And lots of research was done on Zika virus. It was a mosquito-borne virus, which means when mosquitoes bite, you will actually get the disease. But that didn't have alarmed people. After all, it will come 1 week fever, it will go away. And maybe you can protect, but whatever it is. But actually it turned out that it spread through the entire Brazil. Half the people of Brazil got infected. But if a pregnant lady got infected, the child born, 1 in 10 cases, suffered from some kind of microcephaly. The disease is called microcephaly. It is incomplete development of the brain. The child would be retarded. This was a very alarming news. You see, if you suffer for a week, no problem. But if a child is born mentally retarded, it's a big problem. Particularly when people, great sportsmen from all around the world come. See here, this lady has got infected with Zika virus. Can you see the symptoms? It's really not nice. You suffer a great deal. But it stays for a week and goes away. So if it comes to men, there is no problem. If it comes to women who are not pregnant, there is no problem. But if it is a pregnant woman and it comes, it will affect the fetus. Then it is a very great danger. Then immediately people started doing research. And in the United States, they started looking at Zika virus using electron microscope. So this is an electron microscopic image of Zika virus. Can you see these particles? And these boxes are drawn by a computer, not by a human being. The computer has scanned the picture and located where the virus particle is automatically. This is the image processing, what I was talking about. And it has boxed all the virus particles. And because now these virus particles are in different orientation, some is standing erect, some is sleeping, some is inclining. You have various images, two-dimensional images of the same virus. Putting it all together, can't you make the three-dimensional structure? I told you the methods have already been worked out. Although it will be at the scope of this class, and so the three-dimensional structure was determined using electron microscopy. See, this is the three-dimensional structure of the Zika virus. 3.8 angstrom cryo-EM structure of methyl Zika virus. It was published in 1917, last year. It is we come to the contemporary research. What is the use of doing this Zika virus structure? It just turns out that on the Zika virus surface, there is a sugar molecule. That is the sugar molecule that you see here. And that sugar molecule is very essential for Zika virus to recognize human cells and infect. So if you can block this, you can actually cure Zika viral infection. So you see, discovering the structure is a method of drug discovery. So it is obviously of great importance. And the whole work could be accomplished in 1 year, So cryo-electron microscopy now is a very standard tool for looking at structures. But it just turns out that if the structure is very large, you can actually use cryo-electron microscope easily and do the structure. But if it is very small, it becomes very difficult because it's essentially microscopy, you see. The larger it is easier to see. Even in an optical microscope, if you want to see a cockroach, you can see very easily in a very small microscope. But if you want to see bacteria, you need a much more powerful microscope. Like that, larger the structure, the easier the electron microscopy is. But X-rays, it is the other way around. The larger the structure, the more trouble you have. So they are really complementary. So there are two techniques for us to see the world of atoms and molecules. Now you see in 2002, there were almost, this is the time I think you were born, or no, you were not born, a few years afterwards you were born. 2002, there were almost no structures determined using electron microscopy. So electron microscopy was born along with you. When you were born, electron microscopy was born. Today, you see, can you read this? Can you read this? What is that? 5K, what does it mean? 5,000. That is 2016, not 18. Now we need more than 10K. 10,000 structures have been determined using electron microscopy. See, when you were born, no structure. When you are 18, 10,000 structures. That is how science progresses. It is not a linear motion. It is a highly accelerated motion. It also tells us that extremely fast we can become left out. You know, my scientific career is almost over. I retired some time ago. But if I don't keep up with science, very soon I will hear science will be there. You know, you will have to be running all the time to keep up with science. Which really means that we have to work very hard to keep ourselves scientifically accepted. See, if you want to demonstrate how electron microscopy has developed, in the beginning you could only see only rough shape of molecules. Today you can see atomic structure of molecules. So the power of electron microscopy has increased from mere imaging to atomic structure in just 15-20 years. You know, it's absolutely amazing development. Of course, you see, the bigger the easier with electron microscopy, the bigger the more difficult with X-ray diffraction. So electron microscopy is very good for virus particles, not so good for proteins. Proteins are already very large molecules compared to organic molecules. But X-ray diffraction is very powerful here and much more difficult in this domain. So the two are very complementary techniques. Still, of course, in X-ray diffraction, you can actually see each atom of a molecule. This is the structure of a protein determined by my colleague Ramakumar at the Indian Institute of Science. See, this is a protein called silanase. And you can see every atom of that silanase molecule in the X-ray diffraction so-called electron density map. In other words, X-ray diffraction is still the more powerful technique, but electron microscopy is fast approaching electron diffraction in terms of its power to reveal the structure of molecules. So in summary, I have told you two techniques. One is X-ray diffraction and another is electron microscopy. X-rays are electromagnetic radiation. Electron microscopy uses the wave nature of electrons and constructs a microscope. One is a microscopy, another is a diffraction technique. Both of them reveal the structure of atomic work. And that is how all ideas of your atomic physics or, chemical bonding. In chemistry, you learn a lot about chemical bonding, shapes, size, and conformation of molecules. Isomerism and all that. All that knowledge has been validated only through these two techniques. Thank you very much for your attention.
Thank you, sir, for the inspiring lecture. Any questions from student side?
Yes, go ahead.
So if air is really an insulator, so then how did Nikola Tesla pass wireless electricity for just a small amount of time?
No. If air is an insulator, what was the question?
So how did Nikola Tesla pass wireless electricity for a small amount?
No. The electromagnetic waves pass through air. Electricity does not pass through air. Electromagnetic waves are not the same as electricity. They are a combination of electricity. They are oscillations of electric and magnetic fields. They will propagate through air, through vacuum. But electricity does not pass through air. But actually lightning is an electrical current. But there the voltage is millions of volts. And it is moist air. Dry, not dry air. If the air is moist, its resistance drops. And if the voltage is millions, it can pass through. So lightning occurs. Then electricity passes through air. But you can, under normal circumstances, if you reduce the air pressure to 10 power minus 7 atmospheres and apply something like 50,000 volts, then it will pass through air in the laboratory.
the atoms under microscope?
No, because the atoms are much smaller than the wavelength of light. That is the whole point of the lecture. That anything smaller than the wavelength of light, you cannot see no matter how powerful your microscope is.
So just like we use X-rays for the molecules, so could we use other wavelengths?
Which, for example?
Maybe gamma rays.
Yes, but how do you produce gamma rays? It's almost impossible to produce gamma rays of any intensity. See, gamma rays can be obtained from radioactive elements, but the intensity of gamma rays is very, very low. You can produce very intense X-rays. You cannot produce very intense gamma rays. If you can use. For example, neutron waves you can use. Neutrons also have a wave character. So there is neutron diffraction. You know, Chidambaram, who was the advisor to Prime Minister of India, scientific advisor, is an expert in neutron diffraction. But to have neutrons, you have to have an atomic reactor. You cannot do it in Belgavi. You can do it in Tarapur, in Bombay, where they have a nuclear reactor, you get a neutron beam. Even Tarapur neutron flux is not very good. You will have to go to France, much bigger nuclear reactor. You get a neutron flux of sufficient intensity. So it's very difficult to produce any kind of rays of your choice. So gamma rays are very difficult to produce. So they are not used. If you can produce enough gamma rays, you can use it. Yes.
Why the negative and positive particles attract to each other?
What?
Why the negative and positive particles attract to each other?
Why? You see, actually, you cannot ask why there two objects of mass attract each other. That is the law. You cannot ask why a law exists. See, gravitation is a law, Newton's law of gravitation. Why does sun attracts earth? Sun attracts earth, that is the law. That is our observation. There are two types of charges, they attract each other. That is the law, that is the Coulomb's law. You cannot say why, there is no answer to that. That is in nature.
Why some diamonds had some colors various?
Huh?
Diamonds had some various colors.
Diamond, that's because of the impurity. Pure diamond has no color, it's very clear. When there are impurities, they scatter light of specific wavelengths. Then the diamond gets color. There are two ways diamond gets color. So most of the time, a colored diamond is called defective, and its value in the market is lower. But certain type of contaminants give very attractive color to diamond. Then it can actually make diamond more expensive. It's actually a dirty diamond, really, if you want to say so. But dirty in a very pleasing way. So it has a much better color. So generally it is due to impurities. Pure diamond is colorless. Here.
Sir, how the crystals are a symbol of the vanity?
Vanity, because you see Kohinoor diamond was stolen by Britishers. Why would they steal it if it is worthless? People used to fight, Muhammad Ghazni Muhammad raided India many times. Do you know what he looted? Gold and diamonds. So obviously it is full of vanity. And if some woman has a diamond necklace, she will be very proud. And she will look down on people who don't have diamond. So it is a symbol of vanity. It has always been a symbol of vanity. Right?
Thank you, sir.
Yes.
Sir, due to simple microscope, we could zoom things or images to a small scale. Due to electron microscopy, the zooming increase. Is it possible to see more zoom that quarks or nucleus of atoms?
No, because you see, wavelength puts a limit. If you can have a wave which is smaller than the nucleus, you can zoom into the nucleus. But electron waves do not have that short. See, nucleus is so much smaller, almost 100,000 times smaller than the size of the atom. See, Atom is 10 power minus 8 centimeter. Nucleus is 10 power minus 15 centimeter. It's much, much smaller. So you cannot zoom in on the nucleus. You have to use a wave whose wavelength is smaller than that of the nucleus. What wave can you produce? Even gamma rays don't have that radius. It's longer wavelength. So you cannot zoom into the nucleus. But how can you see the nucleus? Well, you cannot see it very well, but it's a little beyond scope of this class. Neutron diffraction can be used to locate precise positions of nuclei, because it's the nucleus that interacts with neutrons, not electrons.
Hello, sir. Good afternoon. Sir, they said that the gems are like they have connection between like planetary system. Is that true?
Which one?
So like the gems, like the precious stones. So they have connection like between.
I have a nice, very wonderful slide for that. First, to answer your question, no. The answer is no. But, sit down please. See, do you know sun is ruby? Sun is identified as ruby. Diamond is identified as Venus. And sapphire. You see, each planet, if you look at the planet, it has a color. Sun appears red in the morning and evening. Ruby is red. Venus is the brightest of the planets. Belly, we call it in Kannada. And that is identified as diamond. So there is a lot of sense in what people call names of each planet, associate crystals of each planet. You know, Mars appears mildly red. I think Mars is identified in emerald. I don't know, I'm not so sure. So each planet is identified by a color which represents the color of the crystal. To that extent, the naming is meaningful. But to say that that has anything to do with Venus, has anything to do with diamond is a foolish thing. There is a resemblance of how that appears. It is serious. It is a star, like the brightest star in our galaxy. So you can give a special place for it. But beyond that, there is no other meaning. But I don't want to believe in ancient knowledge. They knew that these have characteristic appearance, and crystals have characteristic appearance. They do one-to-one correspondence. That moon is pearl. Moon is associated with pearl. You have seen pearl, right? It's so nice moon and it's white. So it's a moon. At least from here it looks moon. Maybe if you land on a moon surface, it will not move at all. But from Earth, it looks like a smooth, round, there are very many children's songs which tell you who put the ball in the sky. So it is much, if you go down to the moon, it doesn't look spherical at all. Only from a distance it looks very smooth spherical. But anyway, there is a meaning to associate with planets with certain dimensions. But there is no spiritual meaning or some effect on your luck or anything. If somebody says you have to wear a emerald because you are born in such a star or planet, it's nonsense. I don't think there is any truth in it. But association of planets with certain crystals has some meaning.
Sir, there is any remedy for Zika virus?
Remedy? As of now, no.
So it can be cured by inoculation process?
No, there is no inoculum. There are many viruses for which there is no cure. Common cold virus has no cure.
So why does protons and neutrons doesn't participate in chemical reaction?
The proton participates. Proton participates. Again participates. See, actually the electron that really participates in some sense because they are the shell electron. But you see, hydrogen nucleus is a proton. And that nucleus, you see, the hydrogen atom, the hydrogen nucleus can pull hydrogen. See, proton participates by pulling out electrons. Take for example sodium chloride. See, sodium and chlorine is ever ready, nucleus of the chlorine is ever ready to capture the electron. This is the nucleus that captures an electron. Not the electron. Electron is triple electron. But the nucleus will pull an electron so that it becomes Cl minus. And the true sodium with the last electron becomes Na plus. And sodium chloride becomes an ionic crystal. So protons participate in chemical reaction. Then indirectly, by influencing the desired, is outer shell electron, determines the chemical property. But changes in the outer shell electrons is affected by the nuclear charge. So, in that indirect sense, protons are important.
So you have said that by finding out the structure of a virus, it is a very big step in curing it. Then why is it so difficult to cure like a stage 4 cancer or something?
So, cancer is not caused by virus. Although some type of cancers are caused by virus. Polyoma virus causes cancer. But many cancers, or most cancers, are not caused by virus. They are caused by uncontrolled division of cells. So you have to control the division of cells. There are many drugs which actually kill cancer cells. So cancer is curable. Only the advanced cancer and certain type of aggressive cancers it is difficult to cure. For example, you see, if breast cancer is detected in the very first stage, almost survival is guaranteed. It's completely curable. They get some type of cancer in the stomach are 100% curable if they are detected early. So cancer has a cure. But eventually everybody dies. So if the cancer is very metastasized, we say, it has spread to all parts of the body, then no medicine will actually cure. So you see, not like yes or no answer. There is cure to some extent. There is no cure beyond that point. So, for a large number of cancer patients, the survival is guaranteed. HIV, for example, you get infected with HIV, you can live up to 70, 80. Is that not giving a lease of life? Without medicine, you would have died in 10 years. Now you live for 50 years. So that is like heart problem. People who have heart problem would have died in their 50s or 60s. Now they will live for 3 years. Eventually they will die. So, these are very cure, but not 100%. There is no 100% cure. All of us, you, me, included, we die someday. Data City, Dhruva Murthy. There is no escape from death for anyone. Eventually death will win. But we can postpone death as much as possible. How much? See, when we got independence, the average lifespan, life expectancy in birth was 27 years. That means, on an average, all our fellow countrymen were living no more than average 27 years. Today it is 70. Haven't we pushed death? We have. This is the real benefit of life.
Good evening, sir. Sir, we know that protons are arranged in the center of the cell. Sir, why don't they repel each other?
Well, because there is a force called nuclear force that holds them together. It is more than the repulsion. Protons repel each other, but nuclear forces make them attract each other. There are two opposite forces. There is also a repulsion, there is attraction. The attraction is more than repulsion, so they are stable. But when the nucleus becomes larger and larger, the repulsion becomes proportionally larger compared to attraction. So the nucleus becomes less and less stable. Beyond lead, the nucleus is already wobbling. It becomes radioactive. It spontaneously breaks down.
So then, how is this nuclear force generated?
Huh?
So how is this nuclear force generated? Like how is it created?
Oh, all forces are generated. This is a standard model of physics. There is a particle that is exchanged between these two. And those particles mediate the force between them. This is subject matter whole of field theories in physics. Still advanced physics stuff. How are these forces generated? Even gravitational force is supposed to be generated by a particle called graviton. But that has not been discovered. Gravitational waves were discovered just a few months ago. But that is the first step towards discovering graviton. But obviously, gravitons are exchanged between Earth and Sun, and that establishes a force. Nuclear force also is supposed to have been generated. Is supposed to be generated in a similar way by exchange of metons.